Hi, I'm Bob. We have solved the problems on the simple linear regression model over the past 3 videos. Today, let's do the computer exercises. At the end of Chapter 2, the simple regression model in the textbook Introductory Econometrics, the 7th edition. I use Stata to do the exercises. Let's look at the first computer exercise. Here's the first question. After we use the command use to load the dataset, we can type describe to obtain the information about the variables. The variable P rate is the participation rate, and the variable M rate is the match rate. We use summarize to find their sample means. The average participation rate is 87.36%. The average match rate is 0.73. The second question, we use the command regress to run the OLS regression. The slope estimate is 5.86. The intercept estimate is 83.08. We can write the estimated equation as P rate hat equals 83.08 plus 5.86 times M rate. The sample size is 1,334. The R squared is 0.075. The third question. The intercept implies that if the match rate is 0, the predicted participation rate is 83.08%. The slope estimate suggests that if the firm's match rate increases by $1, the workers' participation rate will increase by 5.86% on average. The fourth question. The predicted participation rate is 103.6% when the match rate is 3.5. It is not a reasonable prediction. The participation rate could not be above 100%. Using linear regression to fit a nonlinear relationship could lead to an unreasonable prediction, especially for the explanatory variables with extreme values. Besides, a simple regression model has only one explanatory variable. Some relevant factors could be omitted from the model, and it results in bias. So the estimated equation does not fit the data well, and some fitted values are very different from the actual values. The fifth question. The R squared is 0.075, meaning that only 7.5% of the variation in the workers' participation rate can be explained by the variation in the firm's match rate. It is a low R squared. It suggests that the simple linear regression model does not fit the data well. Let's go to the second computer exercise. We describe the dataset and find the variables salary and CEO10. Salary is annual compensation in thousands of dollars, and CEO10 is the years as CEO in the company. For the first question, we use the command summarize to find the sample means of the variables. The average salary is $865,864. The average tenure as a CEO is 7.95 years. For the second question, the number of CEOs in their first year as CEO is 5. The longest tenure is 37 years. For the third question, we regress the log salary on the CEO tenure. The estimated equation is log salary hat equals 6.51 plus 0.0097 times CEO tenure. 1 more year as a CEO increases the salary by 0.97% on average. Notice that when the outcome variable is in the log term and the explanatory variable is in the level term, the slope coefficient indicates the percentage change in the outcome variable for 1 unit change in the explanatory variable. Let's do the third computer exercise. For the first question, we regress sleep on total work. The estimated equation is as follows. The intercept is the time for sleeping if the individual does not work. She will sleep for 3,586 minutes per week. That is about 8.5 hours per day if she does not work. For the second question, if total work time increases by 2 hours per week, that is 120 minutes, the sleep time is estimated to fall by 120 times 0.15, that is 18.1 minutes per week. It is around 2.6 minutes per night. It is a small effect. Let's go to computer exercise 4. It asks us to estimate a simple regression explaining monthly salary in terms of IQ score. For the first question, we use the command summarize to obtain the sample means of salary and IQ scores. The average wage is $957.95. The average IQ score is 101.28. The sample standard deviation is 15.05. For the second question, we regress wage on IQ. The estimated equation is as follows. A 1-point increase in IQ raises wages by 8.30 constant dollars on average. The wage is predicted to increase by $124.55 for an increase in IQ of 15 points. The R squared is 0.096. Less than 10% of the variation in wages can be explained by the variation in IQ scores. For the third question, a simple regression model for a constant percentage change in the outcome variable is to use the log term for the outcome variable. We regress log wage on IQ scores. The estimated equation is as follows. If IQ increases by 15 points, the wage will increase by approximately 13.2%. Now we are in the computer exercise 5. A constant elasticity model is a log-log simple regression model. Both the outcome variable and the explanatory variable should be in the log terms. The slope parameter is the elasticity. We regress log R&D on log sales for the second question. The estimated equation is as follows. The slope coefficient is the elasticity. The estimated elasticity of R&D with respect to sales is 1.08. It implies that a 1% increase in annual sales raises annual expenditures on research and development by 1.08% on average. Let's go to computer exercise 6. For the first question, a diminishing marginal effect seems more appropriate than a constant marginal effect. For the second question, the explanatory variable is in the log term and the outcome variable is in the level term. Beta 1 is the change in the outcome variable as the explanatory variable changes by 100%. Since the outcome variable is measured in percentage points, beta 1 is the percentage point change in the outcome variable with respect to a 100% change in the explanatory variable. So beta 1 divided by 10 is the percentage point change in mass given a 10% increase in the expenditure on students. We use the dataset MEAP 93 for the third question to estimate the model. The estimated equation is as follows. For the fourth question, if spending increases by 10%, the estimated percentage point in mass pass rate increases by 1.1 percentage points on average. The average spending per student is around $4,300, and a 10% increase in spending is around $430 per student. The 1.1 percentage point effect on the mass pass rate is not large, but also not trivial. For the fifth question, the maximum mass pass rate in the sample is 66.7 percentage points. We don't worry that the fit value will be above 100. We find that the fit values range from 21 to 30. Let's do the seventh computer exercise. For the first question, the average gift in the sample is $7.44 Dutch guilders. The number of people who gave no gift is 2,561. It is 60% of the people in the sample. The second question. The sample mean of mailings is 2.05 per year. The minimum and maximum values are 0.25 and 3.5, respectively. The third question, we regress gift on mail's year. The estimated equation is as follows. For the fourth question, the estimated slope coefficient is 2.65, meaning that one more mail per year increases the gift by 2.65 guilders on average. We assume that it is a constant return to each mailing when we use the simple linear regression model. If each mailing costs 1 guilder, the charity is expected to make a net gain of 1.65 guilders on each mailing. It is an average value. Some people gave no gifts, and some gave more than 2.65 guilders per mailing, as illustrated in the data editor. We use the command predict for the fifth question to obtain the predicted values of the gift. Then I summarize the predicted values along with the actual values of the gift. The range of the predicted values is much smaller than the range of the actual values. The smallest predicted charitable contribution in the sample is 2.68 guilders. We could not predict zero using the simple regression model. Next, let's do computer exercise 8. In Stata, the function rUniform is for generating uniformly distributed random numbers over 0, 1. I first type set observations 500 to set the sample size. Next, I set the seed equal to 8964 so that the results are reproducible. Then I type generate x equals R uniform, followed by the round brackets. If we don't put any number in the brackets, the random numbers are between 0 and 1. We can multiply the observations by 10 to obtain a uniform distribution with a range between 0 and 10. Using the summarize command, we can see the sample mean and sample standard deviation of x. The sample mean is 4.88 and the standard deviation is 2.86. For the second question, we use the Stata function rnormal to generate 500 errors that are randomly normally distributed. The sample mean is 0.176 and the sample standard deviation is 6.19. The sample mean is not exactly 0 because the sample size is only 500. If we try 5,000 observations, we will have a sample average pretty close to 0. The sample standard deviation is close to the population standard deviation. For the third question, we generate the outcome variable y first. We type generate y equals 1 plus 2 times x plus mu. We have generated the explanatory variable x and the outcome variable y. To run a simple regression, we regress y on x. The intercept estimate is 0.139, far from the population intercept of 1. The slope estimate is 2.213, above the population slope of 2. The reason is that the sample size is too small. If we set a much larger sample size, say 5,000, the estimated intercept and slope are very close to the population values. The fourth question asks us to verify that the sum of residuals is 0 and the sum of the products of x and residual is also 0. We use the command predict to obtain the residuals. After the regression, we type predict mu hat, comma, followed by the option residual. Then we use the summarize command to find the sample mean of the residuals. It is nearly 0. It means that the residuals sum up to 0. We generate a new variable, x mu hat, to store the product of x and residual. We also use the summarize command to verify that the sample mean of it is approximately 0. So the sum of the products is 0. We have confirmed that the equation 2.60 holds. For the fifth question, we have mentioned before that because of the small sample size, the sample mean of the error term mu is not 0. We can see it using the command summarize. It leads to the sample mean of the product of mu and x far away from 0. For the sixth question, we can use another seed say 1, 2, 3, 4, 5, to generate a new sample of data. The primary conclusion will not change. If we set a much higher observation number, say 5,000, we will have a much closer estimate for the intercept and slope parameters, as I have shown you in question 3. Now we have reached computer exercise 9. We use the command described to find the information about the variables. To keep the data for 1996, we type keep if year equals 1996. For the first question, we type count if murders equals 0 and find 1,051 counties without murders in 1996. Using the same command, we find 31 counties with at least one execution. We summarize the executions and find the largest number is 3. For the second question, the estimated equation is as follows. For the third question, the slope estimate is 58.56. It suggests a positive correlation between the number of murders and the number of executions. One more execution is associated with about 59 more murders. The positive sign does not suggest a deterrent effect of capital punishment. The smallest number of murders that can be predicted by the equation is 5.46. For 0 executions, the predicted number of murders is the intercept estimate, 5.46. The residual is the difference between the actual number of murders, 0, and the predicted number of murders, 5.46. That is minus 5.46. For the fifth question, many relevant factors are omitted from the simple regression model. They are contained in the error term. Such unobserved variables include the population of the county, the economic development of the county, the average age of the residents, and the public safety in neighboring counties. The OLS estimate is biased without controlling for these factors. That is, the OLS estimate is not the ceteris paribus deterrent effect of capital punishment on murders. Another issue is the direction of the effect. The number of murders could also affect the number of executions. A county with more murders is more likely to carry out executions. If there is simultaneous causality, and OLS regression picks up both effects, so the OLS estimate is biased. In a word, the zero conditional mean assumption is very likely to be violated in this case. Let's complete the 10th computer exercise. There were 7,430 students in the sample. The sample mean of math scores is 52.13, and its standard deviation is 9.46. The sample mean of reading scores is 51.77 with a standard deviation of 9.41. We regress mass 12 on read 12 and obtain the OLS estimated equation as follows. The intercept estimate has no meaningful interpretation because it is the predicted mass test score when the reading test score is 0. But in the sample, the range of the reading test scores is from 29 to 68. I am not surprised by the slope estimate. It is about 0.7, meaning that one more point on the reading test is associated with 0.7 more points on the mass test. The R-squared is 0.5. 50% of the variation in the mass scores can be explained by the variation in the reading scores. If we regress reading scores on mass scores, we find a similar slope estimate. 0.7 reflects the correlation between the two scores, but not a causal effect of one variable on the other. Eventually, we arrived at the final computer exercise. We used the dataset GPA1 to answer the questions. There were 141 students in the sample. The average college GPA is 3.06. The highest GPA is 4. We use the command tabulate to find the frequencies of each category for a binary variable. Out of 141 students, 56 students own a personal computer. We regress college GPA on PC. The intercept estimate, 3.0, is the predicted GPA for the students without PC. The OLS estimate beta 1 hat is the predicted difference in the GPA between students with PC and those without. In other words, the predicted GPA for the students with PC is 3.0 plus 0.17. That is 3.17 on average. Both estimates are significantly different from 0 at the 1% level. The R-squared is 0.05, meaning that only 5% of the variation in GPA can be explained by the variation in the binary variable whether the students own a personal computer. It is evidence we have omitted many factors in the model. The finding could not conclude that owning a PC has a causal effect on college GPA because many relevant factors are omitted from the model, such as the student's ability, whether the student is diligent, and the student's family background. These variables affect the student's GPA, and they are also correlated with whether the student owns a PC. For example, a student who grew up in a wealthy family is more likely to receive better education before she goes to college than other students, and she tends to have a higher GPA at college. It is also easier for a wealthy student to own a PC. The simple regression model without considering this factor leads to biased estimates. It is not a ceteris paribus effect. The zero conditional mean assumption is not satisfied, and the causal relationship between the two variables cannot be established. Thank you very much for completing the computer exercises with me. I hope the solutions help. See you. Thank you for watching this video and subscribing to my YouTube channel. See you next time.